Hello and welcome to Lecture 3 of Work in Phys 1101. And in this lecture we're going to go back to this idea of a system and talk about whether our system's energy is conserved and what the criteria are for it. And we're going to have to go back to thinking about forces and whether they're internal and external. Some time ago we saw this idea of a system, where we divide everything there is into the things we're interested in, which we call our system, and everything else, which we call our environment. And crucially, we call forces that objects in the system exert on each other. So in this case, I've got a system consisting of objects A and B, and A exerts Fa on B, and B exerts Fb on A. We call those internal forces. And of course, there can be more than two objects in our system, but no matter how many objects we have in our system, the forces that they exert on each other are internal forces. And then forces that are exerted by objects in the environment on things in the system are called external forces. Now we come back to this idea of an isolated system, which we saw when we were studying momentum. We know that forces cause the momentum of objects to change. But all the internal forces in a system have to add up to zero. That's Newton's third law. And so it's only the external forces that change the system's momentum. And so if all those external forces add up to zero, the system's momentum is conserved. It doesn't change. If the sum of all the external forces acting on the system is zero, then the momentum of the system is a constant. That's the law of conservation of momentum. And we call a system like that isolated. And as I pointed out when we were studying momentum, most real systems we think about are not truly isolated, but often we can approximate them as isolated, and that's useful. That's what determines when a system's momentum is conserved. When is its energy conserved? Now, you'll often hear that energy is always conserved, and that is strictly true. But what we really mean by that is that the total energy of the universe is always conserved. So no matter what system you choose, the energy of the system plus the energy of the environment can't change. That's interesting, kind of cool, but when you're trying to solve a problem, it's not necessarily all that useful. So you need to be able to assess whether your system's energy is conserved. Well, we know that forces can do work. An internal force, when it does work, it causes transformations among the types of energy that are in the system. We've seen this when gravitational forces inside the system do work, they cause changes in gravitational potential energy. When springs do work, they cause changes in spring potential energy. But now external forces are going to cause energy to be transformed either from types of energy in the system into some type of energy outside the system, or the other way around. But in any case, they're causing energy to be transferred into or out of the system. So here's a picture of this, just a conceptual picture. Internal forces, forces between objects in the system, cause transformations between types of energy, where we think of these types of energy as being inside the system. And we've seen some energies we call mechanical energy. Those are the kinetic energy and all the potential energies. And those transformations are generally two-way. And friction forces and other forces as well will tend to turn mechanical energy into thermal energy. It turns out it's possible to turn it back, but it's often difficult. So for now, I'm still drawing this as a one-way arrow. But on the other hand, when we have forces due to objects outside the system, and those forces do work, then they will transfer energy from the environment into the system, or from the system out to the environment. Let's see a simple example of this, and it's one we've already looked at before, and at that time we didn't really have the tools to think about it properly. So You have a book in your hand, it's stationary. You raise it some distance, and now you hold it at rest at the new height. We should define our system, and from now on we should be quite careful about defining our systems. I'm going to define it as the book and the earth, and this might strike you as rather strange. Why am I including the earth, but not including the person who's lifting the book? Well, the answer is that I want the gravitational force, the weight, which is exerted by the earth, to be inside the system, because then I know how to deal with it. All it does is transform types of energy to or from gravitational potential energy. And so I can track all the work done by the weight by looking at the change in gravitational potential energy. But see, I don't know how to define a person potential energy. There's actually no such thing. And so it's not so useful for me to include the person in the system, because I don't have a nice convenient potential energy that I can use to track the weight, the work done by the normal force that the person is exerting on the book. So at the moment, we might think that the energy isn't conserved, and the energy of the system isn't. By this definition, the book starts at rest, so it has no kinetic energy. It ends at rest, so it has no kinetic energy at the end. And it goes up, so it gains gravitational potential energy. So the system's energy is not conserved. But we know overall energy has to be conserved. And so all the new energy in the system had to come from the environment, in this case from the person. And so it was the work done, which is work done by an external force, the work done by the normal force acting on the book, that increased the system's energy. So here's what our new energy bar chart looks like. We have an initial energy that's showing nothing. Work gets done on the system, raising its energy, and in the end it has some new gravitational potential energy. And so we'll tend to write this way. Whatever the initial energy is of the system, you add whatever external work is done, and that gives you the final energy. And of course, the external work can be negative. The system can be giving energy to the environment. But either way, we'll write it like this, with the external work on the left side of the equation with the initial energy, and we'll track whether that's energy coming into the system or out of the system by whether this work is positive or negative. So now we can come back to this question of when a system's energy is conserved. In our original definition of isolated, if the external forces add to 0, that's isolated. Well, certainly if all the external forces add up to 0, then the work that they do on the system also adds up to 0. And so if the external forces add up to 0, the system's energy will be conserved. But it's actually possible for the external forces to do no work, even if they don't add up to 0. So we're going to see some examples of that. But this means we have a slightly different condition for energy to be conserved. Really, what we need for a system's energy to be conserved is not that the external forces add up to 0. It's that the work they do has to add up to 0. Let's start with a simple example that we've already seen. So here's the roller coaster going down the hill. And we already know what the energy bar chart is going to look like, but let me be a little more specific. I'm going to define the system to be the cart and the earth. And the cart, I include the person. So that means that if we look at the free body diagram of the roller coaster, the weight is an internal force because it's exerted by the earth. And so that makes the weight an internal force, and we're going to track the work done by weight through changes in the internal energy of the system from one form to another. But I haven't included the track in the system, and it's what's exerting the normal force. So I've made the normal force an external force. However, as we discussed in the last lecture, that normal force is doing no work. And so we know how this turns out. We know that our energy bar chart just has, if I define my axes at the bottom of the hill, then the system starts off with a lot of gravitational potential energy. And because I started it moving, it has some kinetic energy, and it ends up with a lot of kinetic energy. And the only external force is that normal force, and we know it does no work because it is perpendicular to the direction of motion at all moments, and so the system's energy is conserved. But now look at what's going on. The sum of the external forces is not zero. That normal force is the only external force. And that single force certainly cannot add up to zero. So this system is not isolated for purposes of momentum. But if we're talking about energy, the system is isolated. Because the external forces, the sum of all the external forces, does no work, and so the system's energy is conserved. So this illustrates that a system can be isolated for energy and not for momentum, and as we'll see, the reverse is also true. So I'm going to give these different names. Unlike everybody else, I'm going to give these different names. I'm going to call being isolated for purposes of momentum strictly isolated. But when we're talking about whether work is done by the external forces, I'll call that energetically isolated. Now let's look at a case that shows the opposite. Let's say we have two carts, A and B, and they're held together and there's a spring compressed in between them. And I'm going to define the system as cart A and cart B. But I'm not putting the spring in the system. Now I'll just comment, this is an unusual choice. For reasons that I'll explain, you most often do include springs in your systems. But we're not going to this time, just to illustrate this. So we release it. The spring pushes them both away. And because the spring force on either one just depends on the compression of the spring, at any instant the spring force that the spring is exerting on one cart is guaranteed to be equal to the spring force that it's exerting on the other cart. And we know there are no external forces other than those spring forces acting on the system. I mean, there's the normal and the weight, but we know those cancel and add up to zero, so who cares? So all we've got is these spring forces. So the sum of our external forces now is zero. This system is strictly isolated. However, because I didn't include the spring in the system, what we see now is the system starts with nothing, and it ends with a whole lot of kinetic energy, and that is because the spring, which is external, did a whole lot of work on the system. And so here is an example of the opposite of what we just saw. This is a system which is strictly isolated, but is not energetically isolated.